Okay, let's get started. A few things. First, so our lab 5 will be uploaded probably during the weekend or next week. Okay, for lab 5, so it's a small lab, but there are lots of pre-lab you need to do. But in the end, it's not a big lab, but you need to go to the lab for this one, right? I think we may only have like a couple of labs. You have to go to the lab really. So this is one of them because you need to receive a real AM signal to demodulate. Okay, and here we don't have so our SDR cannot receive the frequency of the real FM radio station here. So we need to create our own FM radio in the lab, and then you'll receive it there. Okay, and the other thing is that
Is lab 5 next week?
yeah. Yeah, I think for the labs, especially for the pre-lab, so they are very good exercise. Like it's like homework, right? So, all right, and the other thing is that I received some comment from the midterm review, okay, and they're very good, right? So one comment is to say, so my upload video is too slow, so I need to speed it up. Yeah, I'll try to do that. Yeah, I was planning to upload everything by Thursday, but I got extremely sick on Wednesday after class. I don't know why. I have a big headache, still have it now, so I have to take some Tylenol to make it better. So, but I will definitely try to make it faster. Okay, and so yeah, you don't have to, just use that to give me comments. Just send me comments if you have some, right? So if I did something not right, so I want to correct it right away, right? Instead of waiting, okay? So if I have any comment, just let me know directly, okay? So I think that way I can correct things in a much better way and faster. Okay, let me think. I think that's all I want to say. What I want to say. All right. Yeah, for students who arrive late, I just want to tell you that lab 5 would be in-person lab. Okay, you need to do it in lab because you need to receive radio, from the TA. The TA will create a radio, and then you're gonna demodulate it. Okay, good. Let's review what. Oh, and another comment I got is that. So I think one student say my reviewing is too fast. That I totally agree. Okay, but so we have to do this fast, right? Because we kind of covered that already. So the goal of the reviewing is just to because we have to continue on what we have discussed, right? So maybe you can review it before the class, and and to understand what I said better. Okay, so yeah. So that part is not easy to adjust, right? So I will try to make things more clear, but the review part would always be fast. Okay, so here is just a very brief review of the demodulation for FM, right? So, this is for modulation, not this. Wait. Yes. I want to say this. Yeah, this is just a review of the demodulation for FM. So this is a simple demodulator, right? So we talk about this twice. So I'm not going to say that in detail. So this is just a very easy, but the quality of that may not be very good, right? For this differentiator and envelope detector. So what we covered in the last lecture is the phase-locked loop. So for this, here is a structure of the phase-locked loop. Okay, so basically, this is our input signal now here. And then we pass the signal through first of all, we multiply the signal with 90-degree shift, right? But here we have a different phase, right? The goal is to make the difference between this phase and the input phase are identical, right? And then we use this signal, multiply that. So the goal of this multiplication is to get the difference between this phase and that phase, okay? And then after some filter, for example, one goal of this filter is to filter out the high frequency component, right? And there's some other goals as well, as we're going to see today later. Then we get a difference between, the error of the estimated phase, which is this guy, right? So basically, this error is the difference between this and that. And then we pass through a VCO. So the role of VCO here is the integrator. So after the integrating it, so we get this one, right? Therefore, so the input here is just a a derivative of this guy, right? And then we can see the derivative of this guy, roughly speaking, should be the derivative of this guy, right? And here, the output of this should be this guy, because the derivative of this guy would be just this, right? And then, so this basically means that the PLL can serve as a role for the demodulator for FM, right? But this is just, a byproduct. We can use it as a demodulator, right? But the goal for PLL is not to demodulate FM, right? The goal of PLL is to track the phase, right? We really want to make sure the estimated phase is almost identical as, the input phase, right? So that's the goal of PLL. But we can use that as a demodulator, okay? And so based on what we said, so this is the equivalent diagram for PLL. So basically, let's recall it. So basically what we do is that here is the input phase, and this is the output phase, right? The goal is to make this and that they're identical, right? And then what we do here is that then we multiply a constant here, and then basically what we do is that so we compute the difference here first, and then multiply a constant, and then we get the error term here, right? So this is the error, and then we do an integrator, and then we feed that back, right? So then that will be our estimated phase, okay? And intuitively speaking, let's say, for example, this is a very large number, and say this is very off, right? This is a very small number, okay? So if this is very large, this is very small, then this number will be very large, right? If this number is large after integration, then this number will be large, and then the difference between this and that will be small, right? So that's basically the idea, the rough idea of why PLL work, okay? And so in order to analyze this and to give a precise expression of this filter design, right? Because here we sort of, we assume we already applied the low-pass filter, okay? But there's some other, other function of this loop filter that has to be done, okay? And we want to see, how can we design this loop filter, okay? So in order to do that, then we use the frequency domain analysis. So in particular, when we talk about filter design, instead of using the frequency domain, we use the Laplace domain, right? We use the S-plane, okay? So we compute all the red stuff denote the Laplace transform of each component here, right? So by the way, why we use the Laplace transform for filter design? We don't use Fourier transform, right? So if you just studied the filter design, right, you never seen Fourier transform, right? You only see Laplace, only S, right? So why is that? Right, yeah, that's not our focus here. So basically, Fourier transform is Laplace transform when S equal to j omega. There's only a line here, right? So, but that is not enough. We need other values to determine the property of the filter. Does that make sense? So, okay, yeah. Let's see. The other words. So basically, we need the location of the poles and the zeros to design the property of the filter, right? So we cannot only use Fourier transform. But anyway, so those are the Laplace transform, okay? And then based on that, we can write the relationship between the input, which is this phase, and output and this phase, right? And also the error. Then we can do the analysis, okay? Very nice. And we did some simple analysis. We assume that when Fs is 1, basically we do nothing about the Fs, right? It's called proportional control. So in this case, so we can see it cannot work, right? In this case, it can only work for some phase shift, right? If there's some frequency offset, then it cannot work, okay? So, and we stop here in our last lecture. Yeah, let's continue. the discussion on this. Yeah, let's see. Today is our lecture 22. And hopefully we can finish most of the part before cover in the midterm today. So today, our first topic is to continue talking about PLL. And second, we're going to talk about the PLL in presence of modulation. And then we're going to talk about super heterodyne receiver. Yeah, we'll give you a very brief introduction on what the meaning of each topic is. And then we'll have one part of applications, so that probably will be covered in the next lecture. Yeah. All right, yeah, let's see. Yeah, let's redraw the figure. Yeah, let's redraw the figure. So basically for PLL, yeah, the diagram is like this. Okay, and we have a plus here, we have minus here, right? And then we pass that through a constant amplifier. Loop filter here, and this is denoted as Ft, and in Laplace we denote that as Fs. And then we feed it back. Oh my. Via integral k naught. Okay, so that's basically the procedure. So now we have some notation here. So yeah, now we only use the Laplace transform. So I just give the Laplace transform notation. So here is theta s, here is theta hat s, and here we have an error term. So that's es equals to kp multiply theta s minus theta hat s. Right, and we denote that as fs. Okay, and for this integral operator is k naught over s. Right, so yeah, this is what we did in the last lecture, and from here, so we can work out the system equation to get what the error look like. Right, so basically, this error es will equals to kp over 1 plus k0 kp over s fs and multiply theta s. Okay, so this is how the system equation looks like. So if you don't recall this, just check the notes from the last lecture. Right, we derive it in very detail. Okay, and then we assume that theta s is, so follow this error model, it equals to delta omega times t plus phi naught. So where this phi naught is the fixed phase offset. And this delta omega is the fixed frequency offset. Okay, and and because of that, so we can write, right? So from here we can write theta s So that equals to delta omega over s squared plus phi naught over s. Right? So we can do the Laplace transform of this and get this. Okay, this is how we get it. Okay, so any questions so far? Yeah, this is what we covered in the last lecture. Okay, and now our goal is to make sure that when the error term goes to 0, so basically what we want is that as time goes by, so when this loop is running for long enough, we want this term is 0, right? ET is nothing but the time domain signal of ES, right? Here is ET. All right, so we want that goes to 0, okay? And so the only thing we can change here is this Fs, right? So we're gonna pick an Fs such that this is 0, okay? And we tried one kind of Fs, which is doing nothing, right? So basically, the first case, the first case we tried is called the proportional control. So basically, it means that Fs is 1. Okay, so if Fs is 1, then so we cannot do it, right? So this part will not go to 0. Right? The way we do that is to show somehow when s goes to 0, s times es, so this has to be 0. Okay, we want to make sure this happens. But when Fs is 1, this cannot happen. Okay, so now I want to try a different Fs. Okay, so can you think another kind of what kind of Fs we should try, right? 1 basically means that we don't do anything there, right? So it basically means that it's not strong enough to make the difference between this and that small. Right? So we have an integrator here, right? Integrator said, okay, so if the difference of this will be bigger, and then we do an integration here, and then the difference between this and that will be getting smaller. But since it's not enough, right? But would this idea work somehow? It should work, right? Yeah, but if this integrator is not strong enough, then what should we do here? Any idea? How about we adding another integrator? Would that work? Yeah, let's try it, right? So basically the idea is this. So basically the second idea is called proportional add integrator. So basically what we do here is that we let Fs equals to a constant, K1, so which is like this 1, right? We just make it more flexible. Well, that can be used to design the filter. Okay, and then we add K2 over S, right? So we add a constant, and then we add an integrator here, and see whether this works or not, right? Very simple idea. So let's try that. So basically in this case, so we know our expression for ES, which is this one, right? So we just plug this Fs in and see what we get. So basically in this case, our ES equals to Kp over 1 plus K0, Kp over S, and times this one, right? K1 plus K2 over S. Okay, and then times theta S. Theta S is delta F over S squared plus phi naught over S, right? Yeah, let's simplify it, right? See what we can see from it. Okay, so yeah, let's see how we can do this. So basically, yeah, how about, yeah, let's see. So we can use this, multiply that to make it look simpler, right? So basically, let's see. Or, yeah, maybe let's simplify this first, right? Yeah, let's, so here is an s, here is an s, and let's multiply s squared on both sides, right? S squared plus s squared plus, so for the first term, so I have s here, and we times k1, so that will be k naught, kp, k1 times s plus, so this multiply that, we have s here, and then this s will be canceled, so that will be k naught, kp, and k2, right? K naught. Okay. Yeah, this is the first term. Okay, and then so we multiply this by the second term. So second term is we have a s squared downstairs, and then we want to add them up together. So that is delta omega plus phi naught times s. Okay, so let's continue our simplification. So we cancel this s squared here, and we'll cancel that here, right? And then we have kp delta omega plus k0s, phi naught s, and then s squared plus k naught kp k1 s plus k naught kp k2. Okay, so this is our result. But remember, so we need to verify this condition, right? Okay, so we need to multiply s on top of it, right? So basically, yeah, let's compute here directly. The limit s goes to 0. S times es, so that will equals to this multiply s, right? So then we have s squared here, we have s here. Okay, so now let's see, when s goes to 0, so will this guy goes to 0? Right? No? Why not? So we have s here, and then we have s here, s here. Okay, so will s goes to 0, will this guy goes to 0? Yes or no? You just put 0 here, then the numerator is 0, right? And then we just need to check the denominator is not 0. Okay, if it's 0 over 0, then we need to use L'Hopital's rule, right? But now we can see the numerator is 0, but the denominator is not 0 because we have another constant term here, right? So this will be 0, right? That clear? Okay, so it means that it works. Okay, so if we design a filter in this way, it's it's a constant plus integrator, then we can make sure the error will become 0. Okay, and so in this way we kind of rigorously prove that the phase lock loop can work, right? Yeah, because before we'll give you some intuition why it can sort of work, but now we prove the error goes to 0 as time goes by. Okay, therefore, so that this works. Any questions? That clear? Are we good? Everybody? Okay, great. So now we're convinced that the phase lock work. Okay. But let's say if we want to use it for example, for the DSCB-SC signal, how can we use it? So can we just directly use it without any difficulty For example, yeah, so this is a kind of a simplified abstract diagram, right? Remember, so what our input is this one, cosine omega ct plus theta I, if you remember. So this is what we have in the original graph, right? And then the output here is maybe another constant, b cosine omega ct plus theta 0 t, and for the phase lock loop, we can guarantee that this guy and this guy are equal, right? And then we're good, right? So this is the whole story, right? So now, if we want to use this to the DSP SCD modulator, how can we use it? So yeah, in other words, so can we use it directly or no? There are some difficulties of using this. So did you see a problem here? Right, for the DSP-SC signal, so we don't, so DSP-SC signal is like what? Let's see, yeah, I'll just write it here. For DSP-SC, right, the transmitted signal is this one, cosine omega ct, let's say plus phi t, so that's a phase, right? So this is our DSP-SC signal, okay? So in order to do the coherent demodulation, so basically we need to know what the phase is, or we need to recover exactly the cosine omega c times phi t, right? So can we use the phase lock loop exactly to see what phi is? Or is my question clear? It's sort of no, right? Yeah, because this is our input signal, right? But now, in order to use it, so this is our input signal. Okay, what's our difference? So here is a pure cosine, but here is a modulated cosine. We have MT here, so that's a troublemaker, right? So how can we use, the idea of PLL for this kind of signal? Right, that clear? Yeah, so this basically, that is what we're going to cover here. So, yeah. I'll just write it here. So this is our second topic. It's the PLL in presence of modulation, and the modulation here we talk about it's basically the DSP-SC. Okay, so we're going to introduce you two approaches. So one approach is to use PLL as a part of it, to get rid of the high frequency component and get rid of the noise. And the other one is another implementation of PLL. Okay, let's see how we can do this. Right, the first one is called squaring loop. Okay, so let's see what we do here. So basically what it does is that let's assume ST is the input DSP-SC signal, right? So basically what we do is that we do the following. Okay, so first we square it. Okay, we do a square of the signal. Okay, and then we band pass it. We use a band pass filter. Okay, that is at 2 Fc. You may imagine, right, because we square it, and then the frequency becomes higher. And then we have a limiter of it. Okay, and after that, we put a PLL here. So you may imagine after the limiter, so what we're going to get is somehow this form, right? But we may have some other additional terms, like noise or higher frequency component and so on. Okay, yeah, I don't have space. So basically after the PLL, I need to put it's called frequency. We do a frequency division by 2. So it basically means that we divided frequency by 2. Okay? For example, if it's 2 times FC, so after this, it will be 1 times FC, right? Okay, and then we're almost done. So after this, so we're going to multiply this with, so after this, so this will give you basically the desired cosine signal you want, okay? And then, after that, we can passing through with an LPF, right? And then you'll get whatever MT that you want, right? So yeah, let's assume this equals to MT cosine omega C plus, when I use phi. Yeah, I'll just, for simplicity, just write it as a phi, because normally we have constant phase shift for the DSP SC signal, okay? Yeah, and you can see the PLL appear here, okay? And let's see how it works. So basically, this could be a coherent demodulator for the DSP SC signal, okay? Yeah, let's see how it works. Yeah. Yeah, let me see. So I may have some notation here. So let me denote signal here is V1, and here is V2. And after the limiter, let's see, so this is V3. And let's see, here's V4. Okay. Yeah, let's compute the signal at each point and see what it looks like. Okay, first, V1. So that signal is ST squared, right? So basically, if we square it, it's MT squared cosine squared omega CT plus phi, right? And we deal with that many times already, right? So did you see this? So where did you see this squaring demodulation? So we should have seen this before, right? So that's kind of a demodulation approach for the SPSC, right? But that is non-coherent. Okay, and as usual, so basically we write that as a cosine. Then basically, what we got is this one, 1 plus cosine 2 omega CT times 2 phi. Right, so this is what we got for V1. And now let's see what is V2. Yeah, remember V2 is here, right? So basically, we do a band pass of 2 FC. So basically, we can get rid of this part, right? Then V2 is very simple. Oh, no, sorry. So we do a bandpass at 2FC. So basically, we want this part. We get rid of the first part. Okay, it's the opposite, right? So basically, V2 of t equals to, so we use this multiply whatever inside is m2 m squared t over 2 cosine 2 omega ct plus phi. Okay. So we get rid of the lower frequency component and we keep the high frequency component, right? Because our goal is to get this phi, right? Okay. So next, let's see what the V3 look like. So now so this is our input, right? So the limiter basically, the limiter does this kind of operation, right? If the changing of mt is too large, then it will limit it to a constant value, and similar for the lower value. Okay, so this can be equivalently understood as this one. So basically, we can imagine V3 of t equals to a constant a multiply a cosine 2 omega ct plus phi, 2 phi, sorry. Okay, and then there's some imperfect part of it, right? So that is, we can imagine those, the changing part, as the higher frequency component. Okay, or high frequency component, not higher. Okay, and then you see, so this is basically pretty much what we want, right? So now the only difference between this and what we really want is this 2 here, right? If we can divide it by 2, divide everything by 2, then we're good, right? And we use this, multiply the original signal of this, right? We have a phi here, and we have a phi here. If we can divide it by 2, then we're good, okay? So now the only thing that is not desired is this part, okay? And remember what the PLL does, right? What the PLL does is that no matter whatever, I remove the PLL, I erase the PLL. So whatever the input is, right, the output of PLL is always a cosine signal, right? There will be no such kind of thing, okay? It turns out that the PLL can get rid of this undesired thing, okay? So that's why we use PLL there, okay? Then after PLL and the frequency divisor, so V4 will be precisely equals to this guy, omega ct plus phi, okay? And then this is what we desired, okay? And then we use that, multiply our input signal, right? And then we can do our coherent detection, and then after LPF, we can get our MT. Okay, is that clear? Yeah, this is how we use PLL to do the coherent demodulation for the SBSC. So it's one way to do that. Okay, you can see, so the interesting part is that, so this is kind of the opposite as what we do for the squaring demodulation for the SBSC, right? Because in there, so we filter out this part, and then we do a square root of the operation to get MT, right? But here we remove this part and then take this part, and then passing that through a TLL to get the phase. Okay, does that make sense? Yes, pretty nice way to use it. Okay, great. Okay, so now let's see another very interesting demodulation. Yeah, remove it. Okay. Second one is called Costas loop. Okay, so that's another way to design the PLL, right? We have seen one way to design the PLL, so this is another way. Okay, yeah, let's see how it works. So, yeah, this is particularly for the DSPSC, this kind of signal. So it's kind of complicated. So the structure is as follows. So we have an input signal. Okay, and then here we have a multiplication, and here we have a multiplication, and let's see, a 90-degree shift here. Okay. Okay, I think that is what it looks like. Okay. Yeah. So we're gonna mark here as V1, and here as V2, and here as V3, and here as V4. Okay. Yeah, let's see what is the idea of it, right? So if you still remember, for the PLL, so the first key part is to get the difference between the two angles, right? Or between the two phases, right? But for the original design of PLL, so the input is what? It's a times a cosine. It's just a carrier, right? But here the input is not carrier anymore. Okay. So this basically tells you how you can still get the difference of the phases using another PLL. Okay. So this is a PLL basically. Okay. So let's see how it works. So basically it works as follows. So yeah, I'll just compute all this signal, and then you'll see how it works. Okay. Again, so let's assume that our transmitted signal ST equals to MT cosine omega CT plus phi. Okay. And here, let's assume that, so here we multiply a cosine signal, right? And the frequency is omega c of t, but there's a phase difference. Normally, we write here as a, for example, theta I. Here we write theta 0, right? But here we write phi. We can just write it 0, right? And the phase difference is just phi, okay, to make our life easier, right? Okay. So if this is that, then let's see what the signal looks like here. So V1 is nothing but MT times cosine omega CT plus phi times omega CT, that's it, right? And here is the phase difference. Okay, and our goal is after all this operation, and make V4 somehow equal to this phase difference phi. And then after this, so this is basically integrator, right? After the integrator, and then we can somehow get, the difference, right? Okay, so now let's see how we can do this. So let's compute it. Okay, so this we have a cosine times cosine here. So this basically equals to 2. And so basically means cosine this minus that plus cosine this plus that. right? And then we have cosine this minus that is phi, right? And add cosine this plus that is 2 omega ct plus phi, right? So this is how the signal looks like in V1. And not exactly, right? In V1, so I think we remove we have a low-pass filter here already, then it means that we don't have this part, right? So this part is gone, okay, in V1. So only this times that, okay? Very nice. And now let's see what the signal look like for V2. Yeah, for V2, so yeah, let's see if here's a cosine omega ct after a 90-degree shift, so this will be a sine omega ct, okay? And then we use this multiplied by sine, so that will be V2. So it's the mt cosine omega ct plus phi, and times sine omega ct. Okay, so that is not hard, right? Because if we have a cosine multiply, cosine multiply sine, so that should be a sine minus sine, right? So this is mt over 2. So we have a sine. This minus that is a sine phi, and then we minus a sine. This plus that, right? 2 omega c plus phi, okay? Very nice. And again, so we're passing that through LPF. Yeah, maybe it's better to denote, to move V2 to here. Oh yeah, it's right? So it's going this way, right? So yeah, we have a LPF here, so this part is gone. Right, so that part's gone due to LPF, and this multiply that is our V2 signal, okay? And then we use this signal multiply this signal, right? V1 multiply V2 to get V3, right? Let's see what is our V3. V3 is so this multiply that is mt squared over 4 and sine times cosine. Right, so that equals to, so sine times cosine equals to half sine 2 phi, right? Then we have mt over 2 divided by 8 sine 2 phi. Okay, do you see where I'm getting? So now we have a sign of the error. Is that good? Yeah, this is what is, if you remember, so what we designed for the original PLL. So this is exactly what we want, right? We want a sign of error, right? When the error is small, then this will be equals to 2 phi, right? So now we have a difference here, right? So this is our V3, and for V4, so this LPF is, so this will behave sort of like an integrator, okay? So after that, so we kind of integral over this. So basically, what we got for V4, this is 3. It's like this. We have a R times sine 2 phi, and of course, this roughly equals to 2 phi. And this R is nothing but the DC component of this guy. Okay, so remember phi is a constant, okay? So now we got exactly what we want, right? It's just a constant, so this is equal to 2R phi, right? We have a constant multiply the error. okay? And then we pass that through an integrator here, a VCO, and then we can get the estimated phase back, okay? And as we go over this, we can see eventually, so this error will become 0, and we can use that for the decoder, for the demodulator, okay? Does that make sense? So kind of not that trivial, right? So maybe you can follow the math, but you need to think. Oh, we're out of time. Okay, we need to think for a minute for the the idea. Okay, so you can feel free to read the book to see how it works. So in the next lecture, we're going to cover the very last part. It's a very small part, and then we're going to talk about the applications, and then we're done for all the material before midterm. Okay, thank you.